Okay, let's just remember what this problem said. It said, find the largest volume of a cone that can be inscribed in a sphere of radius 1. I've taken a minute just to draw sort of a sphere that we can do this. Remember what inscribed means. It means to write in. A prescription is something that you write before, so to prescribe. To circumscribe means to write around. To inscribe means to write in. Now what that means in geometry usually is that if I draw a cone, the edges of that cone have to be touching the sphere. So for example, this is a lovely cone, but it's not inscribed because the edges of the cone are not touching the edges of the sphere. So let's do this. All right. Let me draw one cone that works like this. We'll try to draw a bunch and then we'll redraw the picture just so you can see what's going on. That is at least one cone that gets inscribed in the sphere. It does have a volume. There are other cones we can draw, and let's just talk about what's going on. All right, I could draw this cone. And frankly, the volume of that cone looks like it's even bigger. I can draw this cone, and all of these count as inscribed cones. And we can draw one, I'm thinking really stupid one, really close to the top even, right? I can just draw like this, it touches the edge there, touches the edge there, and it goes like this. Each one of those cones, the orange cone, the blue cone, the green cone, the black cone, are all cones that are inscribed in the sphere, and they want the one of largest volume. Now just for a moment, I want to include two stupid ones that'll actually help. Here is a cone with radius 0, right? It's a stupid cone, but technically it is a cone. It does have a radius at 0. It does have a height, that's 2. It's called a degenerate cone, but it works, and it'll actually help us later on. The other stupid cone I can draw is just this dot at the top, where the height is 0. The radius also winds up being 0, but it's absolutely true that the edges of that cone all touch. We will love that actually later on. Now meanwhile, I just want a generic picture that I can use to start finding some equations that work. So we're going to try to draw, and again, it just does not have to be perfect. All I want is a reasonable picture that I can use to start finding some equations. Let's draw a cone that we know to be inscribed. It's going to look like this, and it's going to look like this, and it's going to look like this. Now, we're asked for the largest volume of a cone. Remember that the volume of a cone is 1/3 times pi times r squared times h. Now for what it's worth, at the end of the semester, if we have time, we'll see where that equation came from. And remember, this is an optimization question. What we want to be able to do is take the derivative of that, set it equal to 0, see where it's undefined, but we can't take a derivative there because there are two different variables. And so what we get, remember, this is called the objective function. What we want is a constraint that we can use. Now, how can I use the constraint? Well, I haven't actually labeled anything in this picture yet. So how about if we do this? I'm going to draw the radius. The radius starts at the very center and goes out to here. That's 1. Now, the problem with that radius is it doesn't touch the cone. So what I'm going to do is draw a much more useful one. I'm going to draw that radius right there and just call that 1. And what else can I draw that's going to help here? How about the radius? Now that's not the radius of the, that's the radius of the sphere, not the radius of the cone. The radius of the cone actually comes right down like this. That's radius right there. The height of the cone goes like this. Now unfortunately, once we get to this, usually what we're trying to do is draw something where we can use the Pythagorean Theorem or trig, both of which work here. If I'm going to try to use the Pythagorean Theorem, unfortunately I don't have a right triangle, so what I'm going to do, and you'll see this a lot, is I'm going to draw this little piece right in here. Right? And now I have a right triangle where I can actually start writing an equation. For example, I can clearly see that r squared plus something squared equals 1 squared. What I don't know is this length right here. Now, how am I supposed to find that length right there? I know that this big height right here is h. I also know that this length right here is 1. Now what that makes, this length right in here is the big length h minus the little length 1. So the little length I get right here is h minus 1. So I'm going to get right here, I'm going to get h minus 1 quantity squared equals 1 squared. And I'm going to use that. Yeah, I haven't decided what my variables are going to be yet, so I'm going to erase this and regret it in just a minute. If they started inventing little whiteboards that like pull over each other, I would absolutely be happy. Now, what do we want to do? The idea with all of these is to somehow solve for something here and plug into here so we get something of just one variable. Now, if I solve for h here, I'm going to have square roots all over the place, and I don't want to plug those square roots into here. That will just stink. So what I'm going to do is solve for r squared instead. So I'm going to solve for r squared. So r squared is going to be 1 squared minus h minus 1 squared. That simplifies a little, and I'm going to do it. So this is 1 minus h squared plus 2h minus 1, like that. And so what I'm going to get, r squared is equal to 2h minus h squared, which is pretty darn simple. And what that lets me do up here is rewrite this volume. Now the volume is now going to only have h's in it, so this is actually going to be v of h. I'll go like that, and I'll start just plugging in. I'm going to get 1/3. I'm going to get pi. I'm going to get r squared, which is not so bad. It's just 2h minus h squared, all times h. Now, this is now a function of one variable. I can start taking derivatives. Now, this is actually one of the very most important steps. The variable is h. What we want to be able to do every time we do a max-min problem is to ask ourselves, is there a smallest possible h and there is a largest possible h? Now remember the picture. Picture looks like this. Yes. H went like this. Now remember, we had a really stupid biggest h that was 2, right? Now that gave us something of volume 0, but it was okay because it was legitimate. And I'm going to get like this. And remember, there's a smallest possible h2 that gave me the dot at the top. And I get like that. And notice, by the way, that the mathematics didn't give us that. The context gives us that. And that's usually what gives us our little closed interval here. Now, every time we get a closed interval, what that's going to mean is when we get to the end, we get to make a little table instead of having to use the first derivative test or make a big graph. This is a wonderful, wonderful thing to have every time you try to do a max-min question, also called optimization question. Look for that closed interval and be very happy that you found one. Now, what am I supposed to do? I'm supposed to find the critical points next. So I'm going to not use the product rule. I can just distribute that. I'm not going to distribute the 1/3 pi. 1/3 pi. What's left here is 2h squared minus h cubed, like that. Taking the derivative now is very simple. The 1/3 pi just keeps going along for the ride. All I get is 4h minus 3h squared. Come on, markers, we can do this, right? Now I'm supposed to simplify this enough so that we can make a sign chart, although we're not going to have to. So I'm going to pull out an h. I get 1/3 pi. I get h. And I get 4 minus 3h. Now once we have the derivative, we're supposed to start looking like that for critical points. Now critical points are where the derivative is undefined or 0. This is always defined, and I'm just going to put a little AD here to let everybody know it's always defined, and then we set it equal to 0. When we set it equal to 0, we get two answers, yes? Let's put our answers over here. We're going to get h equals 0, like that, and we're going to get h equals 4/3. Now, if we didn't have this little closed interval, the next thing we'd have to do is start making a sign chart with 0 on there and 4/3 on there, etc. However, our little statement that says if we have a continuous function, and this is certainly a continuous function, it's just a polynomial on a closed interval, then all the maximum minimum values all have to happen at either the critical points, that's these two, right, or the endpoints, these two. So once we have a closed interval, I'm going to smile, right, because what I can now do, let's see here, is just make a table. We're going to finish with a table. Try not to lose my numbers yet. Not lose my universe yet. Now what do I mean by a table? I mean a table. Right? We just have H like this. And we're going to have the volume like this. Like this. I'm going to have 1/3 pi right here. I'm going to pull an H and an H out so we can see what's going on. So I'm going to have H squared and 2 minus H. Just like that. So that's the volume. Now what am I supposed to put there? I'm supposed to put our critical points, about 0 and 4/3. And I'm supposed to put our endpoints. Well, 0 is also an endpoint, so it's already there. And then I put 2. Now what am I supposed to do? I'm just supposed to plug those numbers in. When I plug 0 into my volume, it turns this part into 0, and that's all being multiplied, so I get 0. Remember, that makes sense, right? That was the stupid cone at the top, which was just the dot. When I plug 2 in, right here, I get 0, so I get 0 for the whole thing, and that also makes sense because that was the stupid cone that looks like a segment. When I put 4/3 in, to a degree, I don't care that much, right? I'm going to get what? I'm going to get 16/9 here, like this. 2 minus 4/3 is 2/3, I think. That's going to look like this. And if someone insists on an answer, I'm going to get 32 pi on the top. I'm going to get 81 on the bottom. Now, why am I happy about having that close interval? I'm guaranteed that one of these is the smallest volume and one of these is the largest volume. Well, that makes this automatically the largest volume. And it happens when H equals 4/3. If they ask for R2, we'll have to solve for R, but we're done for now. I think you get the idea.